Good day, students. This is topic 2, lesson 7, triangle theorems. So in today's lesson, we're going to be talking about 4 different theorems regarding triangles: the triangle sum theorem, exterior angle theorem, equilateral triangle theorem, and the isosceles triangle theorem. So let's look at the examples that we have. So the first example that we have here is a proof, and we're going to prove why all 3 angles in a triangle are equal to 180 degrees. So the proof gives us a triangle ABC. And as we can see, we're trying to prove the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is equal to 180 degrees. So the first part of this theorem states that we have to draw a line through point L, a line L through point B, and have it be parallel to side AC. So this line L that is being drawn is called an auxiliary line. And pretty much we draw an auxiliary line to help us prove something about the figure in the proof. So line L we see is parallel to line or side AC. So let's mark these two as being parallel. All right, so that reason would be the parallel postulate. We know 2 lines are parallel if they are equally distanced apart and traveling in the same direction. We can also use this as a construction as well. All right, statement number 2 says we have the measure of angle 1 is equal to some measure of an angle, and the measure of angle 3 is equal to another measure of some angle, and we need to determine the reason why. So if I look at angle 1, I see angle 1 is located here alongside AC. And remember, line L and AC are parallel to each other. And if I notice here, I also have some transversal that's created. And if I extend this out, we see that transversal is created with angle 1. So if I know that there's a transversal created here, intersecting with the 2 parallel lines, and I see that angle 1 is here, I can state that angle 1, given this transversal, is congruent to angle 4. And the same thing can be said with angle 3. So we have angle 3 here, and I see angle 3 is on the side AC that's parallel to line L. And I notice that angle 3 also has another transversal alongside BC. So if I look at angle 3, I see that angle 3 has a relationship with angle 5. And these 2 angles are also equal. So looking at the relationship of angles 1 and 4, and looking at the relationship of angles 3 and 5, I see that they're both alternate interior angles. And we know that alternate interior angles are equal to each other. So that is the theorem that we're using to state the reason why these 2 pairs of angles are equal. So the third statement says that we have the measure of angle 4 plus the measure of angle 2 plus the measure of angle 5, and those measures all equal to 180 degrees. Well, I can see that to be true because if I look at 4, 2, and 5, all 3 of these angles are on the line L. And if I have angles that create a straight line, that actually creates a straight angle. So if I add them up, that's the angle addition postulate, and these 3 angles create a straight angle. So that's the reason for statement number 3. Statement number 4 states that we can move from statement number 3 and create this new equation where the measure of some angle plus the measure of angle 2 plus the measure of some other angle equals 180 degrees. Well, we stated in statement number 2 that angle 1 was equal to angle 4 and angle 3 was equal to angle 5. So if I'm moving from statement number 3 to 4, I see that 4 can be replaced with the measure of angle 1, and 5 can be replaced with the measure of angle 3. And as you can see, it brings us back to what we originally wanted to prove, that all three angles in triangle ABC, which was 1, 2, and 3, were equal to 180 degrees. And the reason why we can replace these angles is through the substitution property of equality. And as you can see, that concludes our proof for example number 1. All right, so let's look at example number 2. Example number 2 says, match each angle with its corresponding measure, given that the measure of angle 1, which is here, is 130 degrees, and the measure of angle 7 is 70 degrees. And we want to indicate a match by writing the letter for the angle on the line in front of the corresponding angle measure. So we have the missing angles here along the left side, A through E, which is the measures of angle 2 through the measures of angle 6. And then we have these angles of 50 degrees, 60, 70, 110, and 120 degrees listed here. So our goal is to match the indicated angles on the left with the measures of the angles on the right, based on the angle relationships within the diagram. So they already gave us the measure of angle 1 was 130 degrees. So let's try to go in order to see if we can find these angles. So if I see that the measure of angle 1 is on the same line as the measure of angle 2, that means that the measure of angle 1 and the measure of angle 3, the measure of angle 1 and the measure of angle 2 are what we call a linear pair. And we know linear pairs are supplementary. So if they're supplementary, I can take 130, subtract that from 180, and that would give me the measure of angle 2 as being 50 degrees. So the measure of angle 2 is A, and we have 50 degrees as being A. Now, I'm not able yet to find the measure of angle 3, so let's move on to the measure of angle 5, because 3 and 4 I'm going to need a little bit more information. But the measure of angle 5, I can extract some information based on the given angle, and that's angle 7. So angle 7 I see as 70 degrees, and I see that angle 7 shares a vertex with angle 5, and 7 and 5 are opposite of each other. So that tells me that angle 5 is a vertical angle, and we know vertical angles are congruent, making their measures equal. So I can say the measure of angle 5 is D. So let's start crossing out the ones that we've already done. And then I'm going to also write here along the side of how we got our results. So for 50, we said that they were a linear pair. All right. So now that we have some information about 5, let's go back to 3 and 4. So with the measure of angle 3, I see that it is inside of a triangle. 3, 5, and 2, angles 3, 5, and 2 are inside of a triangle. We already know about the triangle sum theorem, that all the angles within a triangle, the sum is equal to 180. So if I have angle 5 and angle 2 as being 70 and 50, I can add these two angles, which is 120, subtract that from 180, and that would give me angle 3, which I know would be 60 degrees. So angle 3 here would be 60 degrees for B. And we can write here the triangle sum theorem. Now, angle 4 I can do two ways. I can either use the exterior angle theorem, because angle 4 is an angle on the outside of the triangle, or I can use the linear pair theorem. So I'm going to use the exterior angle theorem because we already used linear pair. So the exterior angle theorem says two interior remote angles, the sum is equal to the exterior angle. So the two interior remote angles we have is angle 5 and angle 2. So if I add angle 5 and angle 2, that gives me the measure of angle 4. So 70 plus 50 would give me 120 for angle 4. We can verify that angle 4 is actually 120 because angles 3 and 4 are linear pairs, making them supplementary. So 120 plus 60 gives me 180, and that's just a check to know that I'm correct. So we have angle 4 here as being 120, and that was found by the exterior angle theorem. The last one that we need to find is angle 6. And the measure of angle 6 can be found two ways as well. We have angle 7, the measure of angle 7, which is a linear pair with 6. And we have the measure of angle 5, which is also a linear pair with angle 6. Good thing to know is that both of them are 70 degrees, so it doesn't really matter which one we use. So being that they're both linear pairs and they're both 70 degrees, we know that a linear pair is supplementary, and supplementary means that we have two angles whose sum is 180. So if I take 70 degrees and subtract that from 180, I know that angle 6 is 110 degrees. So we have our final angle here of E, which is 110 degrees, and that was found by a linear pair. All right, so let's look at example 3, which says determine the measure of the specified angle. So the angle that I'm looking for is angle PRS, which is this angle that happens to be on the outside of the triangle. So because this angle is on the outside of the triangle, I know that this is an exterior angle. So that means if I notice, I also have two angles on the inside of the triangle, which is angle Q or RQP, and I see that that is a 90-degree angle because it's specified as a right angle. And I have angle P or angle RPQ here that has the expression of x plus 2. So I know that these two angles identified are the remote angles because they are on the inside of the triangle furthest away from the exterior angle. So that means that I can use the exterior angle theorem, which states the two remote angles, the measure of angle Q, added together gives me the remote angle, which is the measure of angle PRS, and that's the angle that we're looking for. So now that I have my setup, I can substitute the values. So the angle Q is 90 degrees, angle P is x plus 2 degrees, and the measure of angle PRS is 3x minus 8 degrees. And here now we're just going to solve for x. So combining like terms on the left, I get x plus 92 equals 3x minus 8. And then subtracting x from both sides, I have 92 equals 2x minus 8. Adding 8 on both sides, 2x equals 100, divide by 2. So we have x equals 50. But my goal was not to find the value of x, my goal was to find the measure of angle PRS. So to find that measure, I'm going to take what I have for PRS and substitute the value of x. So I have 3 times 50, which gives me 105, subtracting by 8, which gives me 42 degrees. So I know this angle right here is 142 degrees. Okay, example number 4, we have another proof, and this proof is asking us to prove the isosceles triangle theorem. So they give us some information here about this triangle ABC, that side AB is congruent to side AC, and they want us to prove angles B and C, and if we know about isosceles triangles, angles B and C would be our base angles. To help us with this proof, I'm going to reflect triangle ABC and create another triangle called CAB. So imagine some line of reflection, and I'm just flipping it open to help us walk through this proof. So I have two congruent triangles. Remember, it's being reflected across this line of reflection. And the first statement says that we have side AB, which is this side right here, is congruent to side AC. Remember, we reflect this triangle, so we have two sides that are corresponding and congruent. And that's given. They gave us that information here in the proof. The second statement says that we have angle A here in the first triangle congruent to angle A in the second triangle. Well, I see that these two triangles share the same exact part, and remember, it's being reflected, so they are congruent triangles. And if I have two figures that share the exact same part, the reason would be the reflexive property of congruence. Okay, the next statement that is stated for number 3 is that side CA is congruent to side BA. Now remember, again, we have two figures here, two congruent triangles, and it's saying here that we have side CA congruent to side BA. Well, I know that's the symmetric property of equality because we just mentioned that here in statement number 1. Number 1, we said BA was congruent to CA, and that was mentioned here in the first triangle to the second triangle. And then now we have statement number 3 stating that CA is congruent to BA again. So remember, we reflected this triangle over this line of reflection, so that would be the symmetric property of equality. The third statement says that we have triangle BAC, which is triangle number 1 here, is congruent to triangle CAB, which is triangle number 2 here. And they want us to give a reason of why these two triangles are congruent. Well, if I think back to the triangle congruency postulates and theorems that I had for the shortcuts, I noticed that both triangles have two corresponding sides that are congruent, and they also have one corresponding angle that's congruent. Also, that angle happens to be in between the two corresponding sides, meaning that the angle is included. So if I have two corresponding sides that are congruent and one included angle, that tells me that is the side, angle, side, triangle congruence theorem. So I've proven that these two triangles are congruent, and anytime that we prove two triangles to be congruent, what does it say about their parts? Well, we already know that two congruent triangles mean that they have corresponding congruent parts. So that leads us to the conclusion of our proof that angle B is congruent to angle C. So that means that this angle B here is congruent to angle C, and this angle C here is congruent to angle B by CPCTC, which means corresponding parts of congruent triangles are congruent. Okay, let's look at example number 4, part B, where we're actually going to use the isosceles triangle theorem to solve this problem. We proved it in part A. For example number 4, now we're going to apply it. So it says find angle P, which is located here. I notice already that I have two congruent sides, side QR and side PR. These two sides are congruent, so that tells me that the opposite angles from these sides are also congruent. So QR is opposite of angle P, and PR is opposite of angle Q. So that means P and Q are the base angles of the isosceles triangle. So that means if Q is 3x plus 3, that means angle P is also 3x plus 3. So now that I have all three of the angles identified in this problem, I can use the information to find the measure of angle P. Well, what do we know about all three angles in a triangle? Well, we know that all three angles in a triangle add up to 180 degrees. So now I can just substitute the values of all three of these angles to solve for x. we already know that angles P and Q are the same exact angles, so I don't have to rewrite them. I could just say 2 times 3x plus 3 plus the measure of angle R, which is 5x minus 2. That equals 180 degrees. And now I'm just going to solve for x. So we distribute our 2 to everything inside of our parentheses, giving us 6x plus 6 plus 5x minus 2 equals 180 degrees. Here I combine like terms where I get 11x and add that together, which gives me 4 equals 180. Subtract 4 from both sides, so I'm left with 11x equals 176. Divide 11 on both sides, so I'm left with x is equal 16. But my goal was not to solve for x. My goal was to find the measured angle P, which we know was 3 times x, which is now 16, plus 3. So 3 times 16 plus 3 gives me 51 degrees. But how do I know for sure that angle P is 51 degrees? Well, I already know that angle P and angle Q share the same angle, so that's 51 degrees, and this one is 51 degrees. We just now have to find angle R. So 5 times 16 minus 2. 5 times 16, I know that's 80. 80 minus 2 gives me 78. And if I add 78 plus 2 times 51, well, ladies and gentlemen, that's going to give me 180 degrees. So that's how I know that angle P is 51 degrees. Okay, so we're looking at our last example, which is example number 5. And we see here that they are asking us to find the length of the indicated side. So the side that we're looking for is side DE, which is located here. However, they give us some information in the problem. They state that angle D, angle E, and angle F are all congruent angles. Well, if I recall, if I have 3 congruent angles of a triangle, that tells me that they are equiangular. This is an equiangular triangle. And if a triangle is equiangular, that means it's also equilateral, meaning that all 3 of the sides of the triangles are also equal. So if all 3 sides are equal, then that tells me that the sides are congruent to each other, meaning that the measures are equal as well. So to find side DE, all I have to do is equal the 2 sides that I already have, equal to each other. So DF is equal to EF. DF I see as 5x minus 12, and EF I see as 3x minus 4. And here now I'm just solving for x, so subtracting 3x on both sides, leaving me with 2x minus 12 equals negative 4. Adding 12 on both sides gives me 2x equals 8. Dividing by 2, where x is equal to 4. But I'm not looking for x. Remember, I'm still trying to find out what DE is. But we already know that DF is equal to EF, which is equal to DE. All 3 of these sides measures are equal to each other. So this x equaling 4, I can plug into any one of these expressions for the sides, and I would still get the same measure. So let's try DF first. It has 5x, which is 4, minus 12. 5 times 4 is 20, minus 12 will give me 8. The same should be true for EF. 3 times 4 minus 4. 3 times 4 we know is 12, minus 4 gives me 8. So that just concludes that we know that all 3 sides of this triangle would be 8. So that means my answer for DE is 8. All right, ladies and gentlemen. So that concludes topic 2, lesson 7. Remember to go to your warm-up activity in your OneNote class notebook to review all of the vocabulary terms from this lesson. And I will see you in class. Have a great day, guys.